Hello, everyone. Welcome back to the Organic Chemistry 1 weekly reviews. So last week we covered NBS, which is a low concentration version of bromination, Br2HB. But when you see NBS, it's going to say NBS-HB. So just don't be alarmed if you see that. It's the same thing. We reviewed parts of a reaction, what an electrophile is, what a nucleophile is, where the solvent is, how to find primary, secondary, tertiary. Because believe it or not, students are still struggling and mislabeling the position of the leaving group. That is very important. If you mislabel it, you might favor one reaction over or one mechanism over the other, which is extremely, it will get you the wrong answer. We talked about SN2 and SN1 in depth, and then I did a SN1, SN2 table comparing the two regarding different factors. So if you missed all that, please check out last week's weekly review video. And I also talked about, how to find out if your nucleophile is strong or weak, and what the solvent means and how it affects the reaction rate. And we discussed what protic and aprotic meant. So this week we're gonna cover E1 and E2, and that should wrap up our chapter 6 mechanisms material. And remember, you also have chapter 4 about your initiation, propagation, termination, as well as free radical halogenation. You also have carbocation, carboanion, and radical stability trends. All of that, please don't forget chapter 4 material. It does come into play even in chapter 6, because chapter 4 is building up the components, and chapter 6 is the mechanism of the reaction and how it actually takes place. So as you can see, we're covering E1, E2 today, and that will finish the mechanisms. And then next week, we'll do nothing but practice problems, and if there's obviously any questions or anything I need to clarify that I've noticed from students who are struggling, we'll get into that. So we have this week, we have next week, and then we have the following Wednesday after that, after next week, you have your exam 2. So I noticed obviously on the day of the exam, you're probably going to be busy, studying or whatever. But I still suggest you guys try to attend either the live session virtually or in person, so you can get a little bit more of a Q&A hands-on review. Most of the times I don't do a exam review, since the SSC already does a full in-depth 2.5-2 hour review already. So I tend to leave that week just for Q&A to whoever shows up. But if not, I'll still maybe just go over some extra problems. And yeah, we also have to talk about chapter 7 and 8, which is the alkenes unit, I believe. And I'm still not sure if it's going to be on your exam or not. I feel like there may be parts of it since you have 4 lectures over it, and then you also have 2 or 3 more lectures after it. Yeah, you have 4 lectures before it, and you have 3 lectures after. So my best guess would be that there are parts of chapter 7 and 8, and really that I would refer to your professor, your specific professor, because each professor may have some changes to the exam. The overall exam will be almost similar, but there might be some parts that are slightly different. Okay? All right, so let's get into it. Again, if you want more hands-on or one-on-one or more questions, feel free to come into peer tutoring during either my times or another tutor's times. We're open Monday through Thursday, 10 to 7 p.m. or 6:30 p.m. And then Fridays, 10 to 4 p.m. and Saturdays, 12 to 4, and that's completely on Blackboard. My specific hours are Monday, 3:30 to 6:30, and Wednesday, 2:30 to 5:30. So if you guys want to come during my sessions, those are the times. All of this information I already talked about in the very first weekly review in the beginning of the semester. So if you want to go back and look at those specific times, go ahead. All right, so let's get started with chapter 6. E1 and E2. Okay. So just like SN1 and SN2, E1 and E2 have some similarities and have some differences. Okay. And just like last week, I'm gonna do a table of the different factors that separate them. Okay. So first off, we are no longer talking about nucleophiles. We are talking about bases. Okay. And then we are looking at strength of your base, and size of your base. And then we have, so let me erase size actually and put special, and then I'll put size right here. Okay, and I'll explain what that means. Okay, so we have E1 on this side, E2 on this side. Okay, let me see if that's big enough for you guys to see. Okay, looks like it should do it. Okay, so again, E stands for elimination. E1 stands for, you know, 2 steps, and E2 is 1 step, I believe. I'm not sure if the steps matter too much, but just understand E1 is similar to SN1, and E2 is similar to SN2 in I guess the number of steps and potentially the reaction diagram as well. Yeah. So we are talking about bases, not nucleophiles. So bases, they like to accept protons, right? So they're going to abstract a hydrogen. So let me give an example right over here. Okay, so let's say I have Br2, and my reagent is NaOCH3 DMSO. Okay, so I am on a secondary leaving group, which is adjacent to a quaternary carbon. So this is a quaternary carbon, and I believe I mentioned this, and if not, you guys will know. Any leaving group or any position adjacent to a quaternary carbon automatically equals no SN2. Okay. Now let's take a look at our reagent. It looks like this is a strong nucleophile as well as a strong base. Okay, so SN stands for strong nucleophile, SB stands for strong base, and this is a polar aprotic solvent. Okay, so all these factors are pushing towards SN2 except for the fact of steric hindrance. So if your reagent and leaving group, or if your reagent is favoring SN2 conditions, but you have steric hindrance, that is the time you look at E2. So all of this will favor SN2 and E2. Okay, so the Na makes it into a strong nucleophile or a strong base because of that O negative charge. And if you're looking at your periodic trends, that is a good O negative is a strong base. So yeah, because we can't do SN2, we're going to have to do E2. And like I said, bases accept protons, right? And we are eliminating instead of substituting, okay? We are not using NaOCH3 as our base to substitute. That would be SN2. So for E2, or elimination in general, you're going to take a look at your adjacent hydrogens, because you have to form a bond between the carbon that contained your leaving group and an adjacent carbon to get, for this to deprotonate one of the hydrogens. And when this leaves and this also leaves, there's going to be an imbalance of charges on both sides. So you're going to put a double bond in between your deprotonated carbon and your carbon that has a carbocation. Okay? So at the end, you should have something that looks like this. Okay? And the reason why we didn't go this way is because there are no hydrogens right here. That carbon already has 4 bonds, so don't make that mistake of putting that double bond on a carbon that has 4 bonds already. Okay, so that's the general gist of like how an elimination reaction works. Now there are differences between E1 and E2. Specifically, the strength, similar to SN1 and SN2, E1 is going to be weak, and E2 is going to be strong. And those differences are going to be similar to SN1, SN2. So apply similar logic to it. There might be a few exceptions here or there. Now, the special case that I have written for both of these is E1 also has rearrangements. So I'll say rearrangement. Okay, so it can also do a hydride shift or a methyl shift. Okay, so if my NaOCH3, let's say in a world that was a weak weak base, then we could have done a rearrangement of a methyl shift where the quaternary carbon is, and gone from a secondary to a tertiary carbocation, and done elimination from there. If that was E1. But because it's not, because it's E2, we went the other way. Now, E2 cannot do a rearrangement just like SN2, but instead it has a special scenario called anti-coplanar. Okay, and all that means is it needs its, one sec. Okay. All that means is it needs the leaving group and the proton that is being abstracted by the base to be trans from each other. Okay, so if my leaving group is on a wedge, my hydrogen has to be on a dash, and vice versa. If my leaving group is on a dash, then my hydrogen has to be on a wedge. Okay, I cannot have leaving group on a wedge and hydrogen also on a wedge. Okay, So there will be scenarios where you have to look at your adjacent carbons and see which of those potential carbons have a opposite or anticoplanar hydrogen to favor SN or to favor E2. Okay? So that's the special case for both of them. Okay? So the strength will determine if it's E1 or E2. Now the size is completely different and separate from E1 or E2. So you can have a small base and you can have a bulky base. So we use the word bulky instead of big because it gives a better representation, visual representation of the electron clouds that is happening. So bulky, steric hindrance, all of this means essentially the same thing. So whenever we have a small base, we are going to put the double bond in a more substituted position. Okay, let me actually write this a little bit bigger. Let's see if I can scroll also to get some more room. Okay. So small and bulky. Okay. Small is going to be the more substituted product, and bulky base is going to have the less substituted product. Okay, sub means substitution, or substituent, not substitution. All right, so some common examples of small bases and bulky bases. Actually, before we get into that, I'll draw what I mean. So this is an example I love using, so I'm going to continue using this. Okay, so I have a bromine right here. And notice I don't have any stereochemistry, so don't worry about E1 or E2 about about like the anticoplanarness. Okay. So if this is my leaving group, when my leaving group leaves, when this leaves, I'm gonna have this carbon be the center point, right? So I can either form a double bond right here, or right here, okay? Basically, any bond, any double bond connecting the carbon that left or has the carbocation, okay? So those are my three options, okay? So let me undo all that. Okay, so between those three options, really there's only two options because there's a line of symmetry here. Whether you go top left or bottom, you're going to get the same position. It doesn't really matter. So we're just going to look at the bottom and the right position. Okay. So if I create a double bond at the bottom position, I'm going to form a more substituted product because my double bond is substituted by three different carbons, which are right here, and right here. Okay. If I create a double bond right here, my double bond is substituted by two carbons, this one and this one. Okay. So there's a name for both of these. So if I do the blue one, this is called Zaitsev. Okay. I don't know if that's German. It sounds German. And if I do the red one, This is going to be Hoffman. Okay. So we call these the Zaitsev product and the Hoffman product. Okay. Sometimes these matter more than if it's E1 or E2. Okay. So as you can see, Zaitsev product is more substituted with 3, and Hoffman is less substituted. Okay. Another way to look at this is Zaitsev is going to be the one that is more internal or inside the structure, and Hoffman is going to be the one outside or external of the structure. Okay. So let's think about why this is happening. If you have a small base, so let's say we have a small base, okay? This small base is able to so this base has, so this small base is able to attack multiple different positions, okay? Whereas this red one, sorry, not this one. So one moment. Okay. Okay, ignore that diagram. Basically, if similar to SM2, a bulky base, you're going to have a harder time reaching those more substituted hydrogens, which are right here and right here, because this is a secondary hydrogen, this is a secondary hydrogen, but this primary hydrogen is more on the outside. So a very bulky block of compound is going to have an easier time deprotonating this proton right here rather than these more heavily electron clouded positions. Okay, so really it all has to do with sterics, which is dealing with stereochemistry. So make sure you always keep that in mind, and that will really help make you understand. Okay. So some common examples of small bases and bulky bases. This is a good list to keep in mind, especially for the bulky bases, because there isn't many examples you will see. For the bulky bases, the most popular ones are going to be something called LDA and something else called terbutoxide, okay, which is a T-butyl bonded to oxygen bonded to potassium, okay, and usually the potassium leaves and you have an O negative, and that is your base that is abstracting something, your proton, rather. Now, small bases, you have NaOH, which is a strong nucleophile and a strong base, okay? And then another common example is H2SO4, okay? Now, H2SO4 is something you definitely want to remember because almost always it will prefer the E1 product, but obviously for this unit and OCHEM in general, you can't take something and apply it to every example you see, because OCHEM is very easy to manipulate the factors and environment, so you have to take it one example at a time. So there is definitely a lot of critical thinking and problem solving in this class. So I know it can be very tough, and this unit can be a little bit confusing with all the different factors and different opinions of which mechanism it should go. But you guys are doing great. Just hang in there. You have 2 more weeks, so you guys still got this. If you feel a little bit behind, obviously just start coming in to get your bases covered. No pun intended. But yeah, so that's the gist of small and bulky base, decisive and Hoffman product. This is very important. I hope this made sense. And I'm going to scroll up to look at the rest of this. I don't know if I can scroll all the way. Let me see. Okay, so I think that's as far as I can scroll. If you guys wanted to take a picture or something. Okay. All right. So let me explain a little bit about the anti-coplanarness with an example now. So I'm going to scroll down. Then I'm going to draw an example. So let's say we have this structure right here. Let's say we have our leaving group right there on a wedge. We have a methyl wedge adjacent to it, and we have a methyl wedge and a methyl dash adjacent to my leaving group. Okay. So my leaving group, and let's say you have to do E2. Okay. Because sometimes they will tell you to go one mechanism instead of you trying to figure out if it's SN1, SN2. They'll just tell you, we want this reaction to follow through E2 conditions. How will the product look like? Okay, so remember, E2 has a strong base, and in this scenario, we don't have to worry about the more substituted or less substituted, because all positions, actually that's incorrect. Yeah, either side will have the same amount of substituents, so we don't need to worry about that. All we tell you is that it's E2, okay? Now if I scroll back up, the E2 special scenario is that it has to be anticoplanar, okay? So what has to be anticoplanar? It's my leaving group and my hydrogen that has to be anticoplanar to each other, okay? And notice how they are 1 carbon away. They have to be right next to each other, okay? So I can't randomly choose, this hydrogen here or these 2 hydrogens here. This is way too far away, okay? It has to be right next to each other. Let me erase all that. Okay, so looking at this is my carbon that, once this leaves, we have a carbocation. But again, the carbocation doesn't matter for E2. Same for SN2, it doesn't matter. Only for SN1 and E1, carbocation matters. E2 doesn't have any rearrangement, so we don't have to worry about going from secondary to tertiary. So don't worry about any of that. All you have to worry about is my adjacent hydrogen anticoplanar to my leaving group? Oh, let's try to erase. Let me just undo this. Okay, so we don't need that. I don't want to confuse you guys. So looking at this carbon right here, my adjacent carbons are right here and right here. So this is a secondary carbon or secondary leaving group. So, oh yeah, real quick. Sorry, I'm jumping back and forth a little bit. Both of these conditions are going to favor 3, 2, 1. Okay, so does SN1. The only one that does 1, 2, 3, or primary, secondary, tertiary, is SN2, because SN2 really cares about steric hindrance because of the way it attacks that leaving carbocation. E1 and E2 do not care about, you know, steric hindrance. It's only if it's a bulky base, then then these bases will care about. But yeah, as far as like the leaving group, we would prefer a tertiary position and then secondary and then primary. Okay. Okay. So once again, those are our adjacent carbons, and then those adjacent carbons each have a methyl of opposite stereochemistry. So that means on the bottom one we have a dash hydrogen, and on the top one we have a wedge hydrogen. Okay. I really hope the microphone didn't pick up my stomach rumbling just now. I have a long day ahead of me. Okay. All right. So my leaving group or our leaving group is on a wedge. Okay. So that means we are looking for a. So if my leaving group is on a wedge, we are looking for a dash hydrogen, which is going to be right here. Okay. So that means we are going to form our product right here. Okay, so a couple of things. First off, notice how this wedge turned into a line. Okay, so why did I do that? Why did I keep this a dash and change that to a line? Okay, obviously there's no one in the room or in the live room, so no one can answer me. So I'll answer myself. Because Shri, this position is sp2 hybridized, or not even sp2 hybridized. There's a double bonded to that carbon now, and whenever we do that, everything is going to be on a plane. There's not going to be any stereochemistry. Okay, well, good job, Shri. That's exactly what I was looking for. All right. I'm sorry, I don't know why I'm doing this. Anyways, so make sure whenever you create your double bond, if there's any stereochemistry positions, you change that to lines. If you do this, because remember, it's multiple choice, right? This obviously could be free response, but most likely it's going to be multiple choice. Again, I don't know the format. The format's always changing, and even between professors, I don't know. Anyways, if you do this, it's going to be wrong. If this was a multiple choice question, I guarantee you they could obviously give this as an option, because some people may forget the fact that this has to be a line. Okay, so this is wrong. Big red X. That never is a good thing. Okay. Now, again, some other bad examples. If you I don't know if this is necessarily wrong, but so this is kind of getting to the gray area. So I don't think they would do this to you, but just be aware that this may occur, but realistically, I think this should be fine. Like if I was a TA and I was seeing this on a free response and I saw this go from a dash to a line, I would say it's okay, but I would leave a note saying I would leave it as a dash. If there's stereochemistry and it's unaffected, just leave it as it is. I feel like that's something people just don't think about a lot. They always think about what's changing and they forget to leave everything else unaffected as it is. They want to either get rid of it or change something or react with it. So just if it's not affected by the rest of the structure, don't leave it as it is. Redraw it completely same. Okay? All right. Let's see. So hopefully that made a little bit of sense. As far as E2, it's highly likely you'll get an example like this. Highly likely. I won't guarantee it because you never know. Now, one more example I want to talk about before I end the video is a scenario where there are no adjacent anticoplanar hydrogens. Yeah, you will have something like that. OCHEM is fun like that. All right, so let's see. I have to think of an example. I believe this is the most common example we use. So you have your bromine right there. That is the worst B I've ever seen. Okay, right there. And let's say you have your methyl right there. Okay, so I have a scenario that looks like this. And again, I'm telling you to do E2. Okay, so you know for sure it's E2. That means I have to look for I'm creating a double bond, I'm getting rid of the leaving group, and I'm getting rid of a hydrogen that's adjacent to my leaving group, and I'm making sure that hydrogen adjacent to my leaving group is anticoplanar. And again, like I said, I'm creating a double bond between the hydrogen undeprotonating and my leaving group. So let's look at our leaving group. Leaving group leaves. I need to stop saying that. Basically, this is the leaving group that leaves. Your carbon is right here. Your adjacent carbons are this one and this one. Okay? So is there a scenario where I can put a double bond right here? Again, there's no one here, so I'm going to answer myself. No, there's not. Okay? The reason why is this carbon already has 4 bonds, so this will have 5 bonds. Okay? Which obviously, big red X, you don't want that. Okay? That's the biggest no-no in organic chemistry. Carbon with 5 bonds is the scariest thing I've seen on Halloween. Okay? So you really only have this option right here. But wait a minute, my methyl is on a dash, so that means my hydrogen has to be on a wedge. But how can that be? Because my leaving group is on a wedge. My only available hydrogen is also on a wedge. Okay? So we have to, it's not going to be no reaction, okay? That's not going to be the answer, okay? Okay. You have to, so don't leave it blank or don't leave it as no reaction, okay? Very rarely, and I say very rarely because sometimes you can have no reaction on a quiz or exam. You'll have that option, okay? Don't ever, or don't quickly resort to that, okay? Most likely there's going to be something you're missing, something you're not getting at, okay? And that something in this case is you have to rotate this bond right here to push hydrogen onto a dash, okay? And we did this already. You guys already have the skill set to do this. At least I hope you do, because it showed up in exam 1. And if you guys weren't able to understand how that works, don't worry, I'll explain it one more time. Okay, so I'm going to redraw the thing right here. And I'm going to label my benzene ring as R, my carbon right there, this carbon right here. Okay, so so this whole R group side does not change. Okay, we are only flipping. So again, I'm gonna do my stereochemistry. We're only rotating these three compounds, okay? I want my hydrogen to go to my dash position. So I'm going to go counterclockwise. So I'm going to put my hydrogen right there, my methyl on a line, and my T-butyl on a wedge, okay? So now, what do we have? We have, again, I'm going to redraw my bromine on a wedge, and I see an adjacent hydrogen. We're good. That's all we needed to do. All we needed to do was rotate that bond because single bonds have rotational symmetry, right? So you can always rotate bonds on a single bond. Okay? So this might be confusing to, what will the end product look like. So let me redraw everything fully. Okay, so I know there's a double bond there. I know there's a T-butyl here. And I know there's a methyl on that side. Okay? So this might look completely weird to this, but I really hope you guys are able to see how I got this product. Okay? I know this is where my double bond is. My T-butyl, I had to rotate it to the wedge position because we're going counterclockwise, and my hydrogen and my leaving group both left. So in order to compensate for those missing electrons, I had to put a double bond right here. Okay? And one other thing is that we already talked about is my T-butyl wedge lost its stereochemistry because I have a double bond attached to that stereochemistry position. Okay, something else you want to really double check at the end of all this is just to make sure you have the right amount of carbons. So so we have 6 right here, 7, 8, 9, 10, 11, 12, 13. We have 6, 7, 8, 9, 10, 11, 12, 13. Okay, I never want to accidentally get rid of a extra carbon. Okay, because again, with multiple choice, you never know. Even if you, so my best advice is, well, not my best advice, but one of my advices for multiple choices is to always answer the question like it's a free response question and try to match it with your answer choices. Okay. Sometimes you might get the question wrong because you didn't do it right. And that's when you have to rely on the answer choices to kind of guide you and to get you to the right answer. But I guarantee you, if you do a lot of practice problems and you get in the habit of taking the exam like it's a free response exam, and then when it comes to multiple choice, all you have to do, you can still take the exam just like how you would take a free response exam. Hi.
Is Mr. Johnson available?
Mr. Johnson?
Yes.
No.
No?
The undergrad dean?
Yeah, the program?
He's downstairs. Is the main office?
Mm-hmm.
Are you looking for the SSC office?
The student success center?
Yes. All right, sorry about that. Someone had a question. All right, but that's actually all I have for you guys today. Next week, I'll prepare a lot of problems for you guys regarding SN1, SN2, E1, E2, maybe Chapter 4 questions as well. We'll see. And if you have time, we'll maybe get into chapter 7 and 8. We'll see. Okay, so I'm gonna scroll up slowly just in case anyone wants to see anything. If you guys need to pause, I don't know if I feel like I'm talking too fast. I didn't mean to do that. So I don't know if you guys are putting me on times half or times 2. I don't know if you guys, if I'm boring you guys to death. But if this is helping, I really hope you guys are benefiting from it. I really enjoy all of this material. So yeah. All right, I scrolled up all the way. Again, we covered E1 and E2 today. We covered all of the rest of chapter 6 and chapter 4 the weeks before this. And next week we'll just do nothing but practice problems, okay? All right, thanks for coming, guys. I'll see you guys next week.